People, in this video I'm going to illustrate how to prove some small theorems in the Rocq proof assistant. So I'm going to prove that addition is commutative and some related theorems. Okay, let's get started. I have got the editor ready, so I'll just start typing and let's see if everything working. I'm just looking what nat is. Okay, saying that nat is a set type. Fine. Okay, first I will get started with I will try to prove that addition is commutative. Commutative in the sense, let me first write it as a comment. Alright, so I will first state the theorem that I want to prove. So I can do that with theorem. Now I have to give a name for the theorem. Let's say add com. Alright, now I will state the theorem now. I will say that for all natural numbers, two natural numbers, I'm naming them a and b. A plus b is same as b plus a. That is what commutativity means, right? So okay, it looks quite silly maybe. I mean, it's obvious for people who know this. I mean, for people who know the basic math, to say it's trivial is the computer should be able to figure it out automatically, but that's not how exactly things work when you are doing proofs, formal proofs in a computer using type theory. And by the way, these lemmas that I'm gonna show in this demo are already present in Rocq. I'm just proving it again just for illustrative purposes. Okay, now I'll enter the proof mode. So as we can see here, I only have the goal now. Whatever I stated, I have it in the goal section, and I want to move the a, b and nat into the context, so I can introduce that into the context with the intros tactic. I'm introducing both a and b. I'm running this command. Okay, now a moved over, as you can see, a moved over to the hypothesis section and the context section, and the goal is still the same, I mean, without the quantification explicitly. Anyway, right, now I'm performing induction on one of these a or b. I'm going with a. So I got two subgoals. I'm starting with the first subgoal. Okay, let me simplify that. Rocq will be able to, simple tactic will be able to, the tactic named simple, this one, this one will be able to infer that 0 plus b is b, but it cannot automatically figure out that b plus 0 is b. So if you run simple, the LHS will reduce to b, but the RHS will remain unchanged. Okay, so at this point it's as if Rocq doesn't know that b plus 0 is b, so we have to prove that as a separate thing. Let me call it add n 0. I'm saying that for all natural number n plus 0 is n. So now I've got to prove that. So proving that, same thing as I did earlier, I'm going to introduce n. Now I'm doing induction over n. Two subgoals. The first one is trivial, too trivial in fact. So I use the reflexivity tactic to say that the LHS and RHS are same. It uses simple tactic under the hood as well, so that goal is over. And next subgoal, I got that Sn plus 0 is equal to Sn. And I do the simple tactic on it. We got something that we can rewrite with. As you can see, the IHN in the context section, and I want this n plus 0 to end up being n in this part, in the LHS part. I have got n plus 0 in the LHS of the goal. I want to rewrite using the IHN hypothesis that I have as part of my as part of my context, and I want to rewrite using IHN. So instead of n plus 0 in the goal section, I should have n. So I'm rewriting from left to right. So n plus 0 will now become n. Right. So now we got LHS equal to RHS. I will say reflexivity, and that's done. Okay, that proof is over. Now that we got this add n0 proof, we can use it here. So I'm rerunning what we had done earlier. Okay, alright, now we can rewrite the RHS. In the RHS section, we can use the lemma that we just proved. Right, out n0. So, right. So n plus 0, now, using n plus 0 becoming n lemma, we can say b plus 0 now will become b. And that's it. That part of the proof is over. Alright, now we got the next. We got to take care of the next goal, the last goal of the induction step. Okay, now we got that goal. I will just do a simple again. Okay, looks like we are going to need another tactic. I mean, another. We need to prove another lemma. It looks like it. Alright, let's get on. Yeah, at this point we need another lemma, so I'm just gonna write it down. Add SB for all A, B, NAT. I want to say that A plus successor of B, which is to say B plus 1, is same as successor of A plus B, which is to say 1 plus A plus B plus 1. Okay, wait, okay, gotta help myself. Okay, I'm gonna do the same thing as we have been doing now. What? Intro? Okay, I have to use intro. Intro can be used only if you're introducing just one element. Here I'm introducing more than one, so I need to use intros. Okay, I'm doing induction on A. First one should be easy. Alright. Okay, the next goal now. Okay, let's see what happens. Right. Now we can rewrite with what we already had. I already have got. I mean, I want to convert A plus SB into S of A plus B. And yeah, now we got LHS equal to RHS, and that proof is done. Right. Now we can come back to what we have been doing and use it. So now I got S of A plus B. Now as you can see here we already got S of A plus B is equal to A plus SB. We can rewrite using that. So we want to write, I think, from right to left. So we will need to use an explicit arrow here like this. And say add A SB, and hopefully, yeah, right. Okay, now we use the hypothesis IHA to okay, that didn't work out well either. I want P plus SA, not. Okay, wait, let's see. S of A plus B equal to B plus SA. And I got, okay, I will rewrite using this here at this point. And I got P plus A and B plus SA. If I instantiate it accordingly, I can have BA to become a sort of, yeah, right, I got it now. And now we got reflexivity, and that part is done. Okay, now we have finally proven that addition is indeed commutative after what would seem like a lot of unnecessary stuff, but it is not exactly unnecessary. That's just the way how proofs with type theory as a basis works in computers. Right, and now that we have proven that addition is commutative, let's try proving that addition is associative. Add assoc, for all A, B, C. So associativity, so there are three names, I mean three numbers at play here. So I want to say if in this case if B plus C, it doesn't matter whether B plus C or A plus B is done first, we'll always end up with the same result. That's what associativity means, right? So right, we'll start trying to prove that. I'll introduce all the numbers. Let me scroll up a bit, yeah. Right, so here we might notice that although we put a bracket, an explicit bracket in our a plus b, it's not shown here because that's the by default addition associate towards the left as far as Rocq is concerned, so that's not explicitly mentioned. If it is not explicitly mentioned, it is assumed that we should be able, you should infer that the default associativity is used, so it doesn't matter. Alright, in this scenario, what I would say is start throwing with induction on the first number. And okay, now we got two goals. And that's trivial. A simple tactic combined with reflexivity can make short work of that. And let's see what it will reduce to. Yeah, right. We can rewrite this with the help of IHA, and I want to transform a plus b plus c into the other one, right? And now we got LHS equal to RHS, and voila, we have proven that addition is indeed associative. Okay, that the stuff that we had planned for addition was just commutativity and associativity.